lecture we are going to see some of the relationships between different modes of convergence. Okay, so the relationships are given basically by these three theorems: theorem 4.1, 4.2, and 4.3. You see that we have skipped the proof of theorem 4.1 and 4.3, but the proof of theorem 4.2 is given, which is a very simple one. So that's why I keep this proof here. But before going into this proof, let us see what this theorem says. So whatever this theorem says, that is given in this particular diagram. So I am not going into the exact statement of the theorem. Rather, I am trying to discuss this diagram so that you can understand what this theorem says. Okay. So first we assume that all the random variables, that xn and x, all are defined on the same probability space, because I am talking about defined mode of convergence, and we have seen that almost your mean and probability, these three modes, means all the random variable needs to be defined on the same probability space. But for the distributional one, for the convergence distribution, I do not need those conditions. But because we are here, we are going to talk about the relationship between these four modes of convergence. So we will assume that all the random variables are defined on the same probability space. Xn for all n defines on the probability space SFP, and x is also defined on the same probability space SFP. Okay, so this picture tells us that whenever we have an arrow, directed arrow, the relationship flow in that particular direction. So that basically means that if xn converges to x, almost surely this implies that xn converts to x in probability. Similarly, if xn converts to x in arithmetic, then x converges to x in probability. And finally, if xn converges to x in probability, that implies that xn converges to x in distribution. Okay, so if a sequence of random variable xn converts to x in almost surely, it implies that there will be a probability convergence, and in turn that implies that there will be a distributional convergence. On the other hand, if I have a arithmetic convergence, then this implies the probability convergence. That means if xn converges to x in arithmetic, it implies that xn converges to x in probability, and in turn that again implies that xn converges to x in distribution. Okay, so whenever I have a directed arrow, that direction the relationship flow. Okay, so one implies other. Now notice that we do not have arrow in different direction. For example, we do not have an arrow here. That basically means in general probability convergence does not imply almost sure convergence. Okay, and one of such example we have already seen in example 4.4, where we have seen that probability convergence is there, but almost sure convergence is not there. Okay, similarly, probability convergence in general do not imply mean convergence, arithmetic convergence, and distributional convergence in general do not imply probability convergence. So that basically means that xn converges to x in distribution. That does not imply xn converges to x in probability. Again, xn converges to x in probability does not imply x converges to x in x almost surely, and xn converges to x in probability does not imply xn converges to x in arithmetic. Okay, fine. Another point, you notice that there is no relationship between these two mode of convergence. Okay, these two modes of convergence, there is no relationship. So that basically means that there are examples where xn converges to x almost surely, but x does not converge to x in arithmetic. On the other hand, there are examples where x converges to x in arithmetic, but x does not converge to x almost surely. Okay, and now we will see all those examples. We will see. So, but first try to understand. Try to just remember this figure. It is not very difficult to remember that almost sure and mean on the top and distribution at the bottom. Okay, distribution at the bottom, and this shows that almost sure and mean are quite strong mode of convergences. On the other hand, distributional convergence is a quite weak mode of convergence. Okay, fine. So let us see examples where basically obvious, this proof of the theorem we have skipped only except the one proof. This proof is quite simple. This is nothing but if xn converges to x in Rh mean, this implies that xn converges to x in probability. Why this is true? It is very easy to check because you that see that if I have to show that xn converges to x in probability, I have to show this probability goes to 0. Okay. Now this probability is bounded by this one. This is by the Markov inequality. Okay. So this probability is bounded by this one. This is by the Markov inequality, and this equality, this probability is bounded by this one for any epsilon greater than 0. Now notice that this quantity goes to 0 because xn converges to x in Rh mean. So this quantity goes to 0, and as probability is always greater than equals to 0, so this quantity has to go to 0, and this shows that xn goes to x in probability. Okay, clear? So this is basically one application of the Markov chain, one use of the Markov inequality, one use of the Markov inequality to show that Rh mean convergence imply probability. Okay, the rest of the two are not very straightforward, so I'm just keeping it here. But those who are interested, you can see any probability book, any little advanced probability book for this proof. Okay, so now let us see some of the examples which actually shows that one mode of convergence does not imply other mode of convergence. For example, the first one shows that the first mean convergence does not imply almost shear convergence. So this example, as we have same sequence of random variable what we have discussed in example 4.4, and we have shown in this example that xmn converges to 0 in probability, but xmn does not converges to 0 does not converges to 0 almost surely. Okay, xmn does not converge to 0 almost surely. That we have seen in the example 4.4. So now in this example, what we are going to show is that this same sequence of random variable converts to 0 in first mean. So if I can show that, that basically says that well, in this example, the sequence of random variable converges to 0 in probability in first mean, and it converges to 0 in first mean. That actually implies that it converges to 0 in probability also. And but we have already shown that this does not converge to 0. This sequence of random variable does not converge to 0 almost surely. Okay, so that this example actually shows two counter example. One is the two examples where one is that the probability convergence does not imply almost sure convergence, as well as the Rh mean convergence does not imply almost sure convergence. Okay, so let us see why this Rh first mean convergence is there. Very easy to show, because here our x is 0. Because our x is 0, so I have to first mean convergence. I have to check whether the expectation of mod of x mn minus x goes to 0 or not. So what is the expectation of x mn minus x? X is 0. That is same as expectation of mod of x mn. And you see that x mn is only non-zero on the interval of length 1 by 2 to the power n. So that basically means that when I take the expectation is nothing but 1 multiplied by the probability of the interval of length 1 by 2 to the power n plus 0 multiplied by the probability of 1 minus 1 minus 1 by 2 to the power n, right? And so that turns out to be 1 by 2 to the power n. Okay, so this expectation turns out to be 1 by 2 to the power n. This quantity goes to 0, and that shows that x mn converts to 0 in the first mean. Okay, fine. I hope this example is fine. Okay, let us proceed. Let us see now that Rh mean convergence, or other way, that probability convergence does not imply Rh mean convergence in general. Again, this example we have talked about earlier. This is n times 1 by n, indicator function of the interval 0 to 1 by n. And we have seen that in this case, xn converges to 0 in probability. This one we have seen in one of the earlier examples. So now if I can show that this does not converge to 0 in Rh mean, or in first mean, I am done. So in first mean, so let us see. So in this case, if you see this one basically nothing but x is 0. So I need to find out expectation of x mod xn to the power r. And xn is always positive, so mod xn is same as xn. So I need to find out the expectation of xn to the power r, Rh moment. Okay, I have to find out the Rh moment. What is the rth moment? Rth moment from here is nothing but n to the power r divided by probability that divided by the length of this interval, which is 1 by n. So n to the power r divided by n plus 0 multiplied by 1 minus 1 by n. So the expectation is nothing but n to the power r minus 1. Now when r equals to 1, this n to the power r minus 1 converts to 1. When r greater than 1, n to the power r minus 1 converts to infinity. So this expectation does not convert to 0, and that shows that xn does not convert to x in the rth mean. Okay, xn does not convert this to x in the rth mean. So in this case, probability convergence is there, but the rth mean convergence is not there. So in general, probability convergence does not imply rth mean convergence. Okay, this example even can be used to show that almost shear convergence do not imply the rth mean convergence. Because in this case, you can easily check that almost shear convergence is there, because the technique is exactly that's what we have used in example 4.1. You take any omega, you can find out n naught such that 1 by n is less than omega for all n greater than equals to n. So that means for any omega in the interval 0 to 1, xn converges to 0. Okay, xn omega converges to 0, and that's why the probability of the set of the collection of omega where xn omega converts to x omega, which is 0, is same as probability of the interval open 0 close 1. And that probability is 1 because we are talking about the uniform probability. Okay. So again, this example, for this example, we have the almost sure convergence that implies on that in turn that it is also the probability convergence is also there, and but the rth mean convergence is not there. So this example shows that almost sure convergence does not imply rth mean convergence in general, as well as probability convergence does not imply rth mean convergence in general. Okay. Let us so now we have to show that only one thing is left, that distributional convergence does not imply probability convergence in general. And this example is a little bit different way. Say that what we did, we start with a random variable x, which is a normal 0 1 random variable. Okay, and but it is all the random x is defined on the samples on the probability space SFP, but it has a normal 0 1 distribution. Okay, what we are doing that for all n greater than equals to 1, we take xn equals to x. So all the xn's are identical. Okay, so all the xn's are a. So what is the distribution of xn? The distribution of xn is phi x. Capital phi x is nothing but the cumulative distribution function of normal 0 1. So for all n, the cumulative distribution function of xn is capital phi x. Okay, not only that, x also has the same distribution function. Not only that, minus x, because normal 0 1, the density function of normal 0 1 is symmetric about 0, so the minus x also have the normal 0 1 distribution. So that means all the xn, x and minus x, all of them have the same distribution function capital X, capital Phi. Okay, so what does this mean? This means that xn converges to x, right? Xn converges to x. In this case, obviously that is true. So example 4.9. So obviously in this case, xn is x, where x follows normal 0 1. We also have that minus x also follow normal 0 1, and that note that phi of so note that our fnx is basically nothing but capital phi of x, because it is basically the same random variable. Xn for all n is true, so this is true for all n greater than equals to 1. And on the other hand, the distribution function of x is also phi of x, and this is same as the distribution function of minus x, because normal 0 1 has a symmetric density function about the point 0. Okay, so this implies that xn converges to x in distribution. That is obvious, because this quantity, this does not depend on n, and this converges to this for this. But along with this, we have also the interesting part is this also, that xn converges to minus x in distribution, because minus x also have the same distribution function. Okay, so we are here mainly consider this part, not the other one. this part is the interesting one in this case. Now the question is that does xn converges to minus x in probability? Okay, that is the question, and now we are going to show that xn does not converge to minus x in probability. We can show it using the definition of the probability comparison. So what we have to check? We have to check whether mod of xn minus of x greater than epsilon, whether limit of this quantity goes to 0 or not. Okay, I need to check whether the limit of this quantity goes to 0 or not for all epsilon greater than 0. So if this limit of this quantity goes to 0 for all epsilon greater than 0, then xn converges to minus x in probability. If not, if it does not converge to 0, or at least for one epsilon greater than 0, then we can tell that this xn does not converge to minus x. Okay, in probability. Okay. So this quantity is same as mod of xn minus plus x greater than epsilon, and because xn is x, so it is nothing but probability that 2 times mod of xn, or mod of not xn, I just write mod of x is greater than epsilon, because xn is also x. Now we know x has a normal 0-1 distribution. We have x as normal 0-1 distribution, so that basically means this quantity is nothing but probability of mod of x is greater than epsilon by 2. That means either x is bigger than epsilon by 2 or lesser than minus epsilon by 2. Okay, so that means it is basically probability that x is greater than epsilon by 2, or probability that x is less than minus epsilon by 2. Note that here epsilon is greater than 0. Epsilon is greater than 0. So that basically means that this is the 1 minus distribution function. So it is nothing but 1 minus capital phi at the point epsilon by 2. And this part is nothing but plus capital phi at the point minus epsilon by 2. Now this quantity is same as 1 minus capital phi at the point epsilon by 2 plus this quantity is same as 1 minus capital phi at the point epsilon by 2. Okay, this is because of the symmetry. Because of the symmetry about 0, the probability here is same as probability here. Because of the symmetry, the probability here is same as probability here. That's why the probability here can be written as 1 minus distribution function at this point. Okay, so this means we have, it turns out to be 2 into 1 minus capital phi of epsilon by 2. Now note that this quantity does not depend on n, and this quantity also not equals to 0 for any epsilon greater than 0. So that means that limit n tends to infinity, probability that mod xn minus plus x greater than epsilon is equals to 2 into 1 minus capital phi of epsilon by 2, and which is not equals to 0, and this shows that xn does not converge to minus x in probability. Okay, and that is basically we try to show here. So in this example, we have seen that xn converges to a minus x in distribution, but xn does not converge to minus x in probability. Okay, and this shows that distribution convergence in distribution in general do not imply the convergence in probability. Okay, this expression is not given correctly. I will let you show. Okay, so this expression is not given. Okay, so this is there. So we have seen different relationships between different modes of convergence, and it is basically based on this diagram. Whenever we have directed arrow, relationships flow in that direction. When we do not have a directed arrow, in general that relationship do not hold. Okay, so we have seen here that distribution in convergence does not imply convergence in distribution does not imply convergence in probability, but one particular condition this is true. If and the condition is given here in the theorem 4.4, it says that if xn converges in distribution to a constant c, then xn converges in probability to c. Okay, so this theorem says that if xn converges to c in distribution as c is a constant, then xn converges to c C in probability also. Okay, so in general, what we have pointed out, in general, xn converges to x in distribution does not imply xn converges to x in probability, but if this x is a constant, then this is true. Okay, and the proof of this one is very simple. The proof basically using the definition we can able to show that. First, notice that because xn converges to C in distribution, that means the distribution function of xn converges to the distribution function of the constant random variable x equals to C, and the distribution function of that is nothing but 0 if x is less than C and 1 if x is greater than equals to C. Okay, so f and x converts to this function that we know. Now we want to show that this probability that mod xn minus c greater than epsilon, this particular probability converges to 0 as n goes to infinity. Okay, so this probability, you see that we can write in these two parts. So this probability is nothing but that xn is outside the interval c minus epsilon to c plus epsilon. Okay, this mod of xn minus c greater than epsilon basically means that xn is outside the interval c minus epsilon to c plus epsilon. So that means basically this probability can be written into these two parts. One is that xn is greater than c plus epsilon, another is xn is less than c minus epsilon. Okay, so now this is basically nothing but 1 minus probability that xn less than equals to c plus epsilon. So 1 minus distribution function at the point c plus epsilon. On the other hand, here the equality is missing. If I have the equality, then it is basically distribution function at the point c minus epsilon. So if I incorporate the equality, the probability will increase. Okay, probability may increase. So that's why I write here this is less than equal. And then the proof is done that 1 is left here. This quantity converts to 1. Why? Because because epsilon is always positive, c plus epsilon always greater than c. So this c plus epsilon belongs to this range. So f and c plus epsilon converts to 1. On the other hand, c minus epsilon always less than c. So that belongs to this range. So f and c minus epsilon converts to 0. So that's why I have this 1 cancel out. I have 0. So that means that this probability converts to 0 in this probability converges to 0, and this shows that xn converts to c in probability. Okay, so this is a very special case that if x is a constant random variable, that means x equals to c equals to probability that x equals to c equals to 1, then xn converges to c in distribution implies that xn converges to c in probability. Okay, but in general, obviously, this is not true. That we have seen with one example. Okay, so using the previous theorem 4.3 and theorem 4.4, combining these two, we can say that xn converges to c in distribution if and only if xn converges to c in probability. Because if xn converges to c in probability, then xn converges to c in distribution, because probability convergence implies distributional convergence. On the other hand, if xn converges to c in distribution, this implies that xn converges to c in probability that we have done in the previous theorem. So combining the previous theorem and theorem 4.3, we can show that this is the if and only if condition, that xn converges to c in distribution if and only if xn converges to c in probability. Okay, with that I stop for the lecture. Next lecture we are going to see some properties of different modes of convergence, and thank you for listening.